Everyone, welcome to our introductory series. Today we're going to be looking at significant figures. In science, in chemistry and physics, we are going to be getting a lot of measurements. So it's very important to know the difference between accuracy and precision. So what exactly is accuracy? Accuracy is how the measurement we obtained is close to the correct value, whereas precision, on the other hand, is how close the measurement we obtained are with respect to each other. So as you guys can see over here, a very common way to depict accuracy and precision is through, of course, with targeted arrows on a bullseye. So as you can see on the left, every single arrow has hit the bullseye. That represents the correct value, so that is very accurate. But on the right-hand side, you're going to see that the arrows simply do not hit the bullseye, but rather are all concentrated to the side of the target, and that of course represents that they're not close to the correct value, but rather they're in close proximity with respect to each other. Another way to actually look at this is, as you can see here, that's the actual value. It's between 2 and 3. So accuracy is how far away you are from the actual value, whereas precision is how close the values are with respect to each other. So how do we measure accuracy? Accuracy is measured by percent error. So that is basically the absolute value of your measured quantity minus the accepted over the accepted times 100. On the other hand, how do we measure precision? Precision is a measurement using standard deviation. In our courses, we are not going to look at standard deviation at all. That is mostly a subject for statistics. So you would see that in your future classes. What we are going to see accuracy. You would have to obtain a percent error, and you would have to compare it with the correct or accepted value. So, what are significant figures? Significant figures are a method of quickly comparing the accuracy and precision between two values. They're not measuring accuracy, it's not measuring precision, because we just saw accuracy is measured through percent error, whereas precision is through standard deviation. So what does that mean? It is simply looking at two numbers and ascertaining which is simply more accurate and precise. It's a measurement of comparison. So imagine we have two students, and both of these students, we assign them a task of them measuring the side of an index card. Now, student 1 obtained the measurement of the side of the index card with a ruler to be 11.0 centimeters, whereas student 2 took their time and they measured it to be 11.0234565 centimeters. Which would you say is more accurate or precise? Student 1 or student 2? I believe I speak for everyone when I would say everybody would pick student 2, because why? There are more digits. In other words, student 2 took the time and obtained more value placement measurements and is therefore more accurate and precise. That is exactly what significant figures, basically do. We are looking at two measurements and say, okay, student 2 obtained a more accurate and precise measurement than student 1. So it's a quick comparison between two values. So what are now the rules of significant figures? It's very simple. Rule number 1 deals with non-zero digits. In other words, anything that is simply not zero. And rule number 1 says all non-zero digits count as significant. So let's look at a couple examples. Let's look at the following number, 4,132. In this case, the 4 counts, the 1 counts, the 3 counts, and the 2 counts, because they're all non-zero digits. So what is that in total? 1, 2, 3, 4. So we quickly say that that has 4 significant figures. Let's try another example, 4.3. In this case, the 4 counts, the 3 counts, because they're non-zero. So therefore, we simply say that this one has 2 significant figures. And let's try one more example. That is 6.78. The 6 counts, the 7 counts, and the 8 counts because they're non-zero digits. So for a total of 3 significant figures. Now, I know they're not the same measurements, but imagine you had to compare the three numbers that we just discussed. So which one would you say is more accurate and precise? The first one, of course, because it has four significant figures. So rule number one is very easy. All non-zero digits count as significant. Rules 2, 3, and 4 have to deal with the zeros and the different types of zeros that we have. Believe it or not, not all zeros are created equal. There are different zeros based on their placement value. We have leading zeros, captive zeros, and trailing zeros. So let's look at the first one, leading zeros. So as you can see over here, the first zeros that you see in this particular number, these are called leading zeros. They are immediately to the left of the first non-zero digit that you see. In this case, it is the 6. So everything to the left of the 6 is going to be leading zeros. Now we move on to captive zeros. Captive zeros, just as the word suggests, they are between two numbers. In this case, we have the zeros between the 2 and the 3. And then finally, we have the trailing zeros. The trailing zeros are immediately to the right of the last non-zero digit. In this case, it is going to be 5. So let's see what the rules are. Rule number 2 deals with leading zeros. Leading zeros never count as significant. Let's look at a couple of examples. Let's look at the first one, 007521. So in this case, the first two zeros are leading zeros, and they therefore never count as significant. So that means 7, 5, 2, and 1, they count as significant simply because they're non-zero digits. So the first example, we have 4 significant figures. Now let's move on to the second example. The second example, we have 0.0035. The first 3 zeros, they're leading zeros. Why? Because they're on the left of the first non-zero digit, which is 3. In this case, again, they do not count as significant. Therefore, only the 3 and the 5 count as significant, and are therefore, we have 2 significant figures. In the third example, we have 0.0000375. Again, the beginning zeros, the leading zeros do not count, and only the 3, the 7, and the 5 counts because of rule number 1. So therefore we say that the third example has 3 significant figures. Moving on to rule number 3, captive zeros. Captive, if you recall, are between two numbers. Captive zeros always count as significant. Let's look at the following example, 37,002. So, you see the 2 zeros in the middle? Those are captive zeros because they're between 7 and 2, and therefore count as significant. So in this case, we have the 3, the 7, the 0, and the 2 all count as significant for a total of 5 significant figures. Second example, again they're captive because they're between two numbers, the 3 and the 5. In this case, they always count as significant, and we have the 3 counts, the 0 counts, the 0 counts, and the 5 counts for a total of 4 significant figures. Now let's look at the last example. Last example combines rule number 2 and number 3. So the first zeros right over there in the beginning, these are leading zeros. So the first zeros to the left of the 4, they never count. So the 4 counts because of rule number 1, the 3 counts because of rule number 1 again, and so does the 9. Now, the zeros between the 4 and the 3 are captive, and therefore always count as significant. So the last number, the 4 counts, the 0 counts, the 0 counts, the 3 counts, and the 9 counts for a total of 5 significant figures. And finally, we go on to rule number 4. These are trailing zeros. Trailing zeros, they count sometimes. Trailing zeros count as significant only when a decimal point is present. It doesn't matter where the decimal point is as long as it is present. So now let's look at 37,200. Let's look at the first number. So in the first number, right, those zeros at the very end, those are trailing zeros because they're immediately to the right of the last non-zero digit, which is the 2. If you scan quickly the number, you clearly see that there is no decimal point. Therefore, they do not count as significant. So only the 3, the 7, and the 2 counts for a total of 3 significant figures. In the second example, now we do have a decimal. It's almost identical in every respect to the first problem, with the exception of the decimal point being present. So 37.200. So in this case, the 3, the 7, and the 2 count because of rule number 1. These are non-zero digits, so they all count as significant. And now the trailing zeros at the end count because a decimal point is present. So in this case, the 3, the 7, the 2, the 0, and the 0 all count as significant because the decimal point is present. Let's look at the third one, 100. Quick scan. You clearly see that there is no decimal point. That means that those 2 zeros at the end do not count. So for example number 3, we only have one significant figure. Let's look at number 4. That is 100, and you can clearly see that there is a decimal point at the very end. So a decimal point is present. Those trailing zeros will count as significant. So in the fourth example, the 1, the 0, and the 0 count for a total of 3 significant figures. And then finally we go to the last example, and we have all 4 rules at play here. So we have 0.00700,700. The first 3 are leading zeros. We said they never count. The 2 zeros between the 7s, those are captive, they always count. And finally, the trailing zeros at the very end of the number, those count because there is a decimal point present. And it doesn't matter where it is, as long as it is present, these will count. So the last example has a total of 6 significant figures. So if you were to quickly compare the accuracy and precision of all the numbers you see on the screen, I believe everybody would say that the last number is the more accurate and precise, simply because it contains a high number of significant figures. Thank you. See you in class.